Hey guys, welcome back to the workshop, and today we're going to be talking about heat treating. What is it, how do we do it, and why? So the first thing I'd like to cover is something I forgot to cover in the last video on choosing which steels to use and how to find out which scrap steels are good. If you haven't checked that video out, I will link it in the description below. But I did say I was going to name a couple of brands that I know 100% create homogeneous steel files. And so I have one here. This isn't the one from yesterday, obviously. It's still full length. This is the one we're going to be using for heat treating today. But this is a Nicholson Wiltshire. Now, Wiltshire was originally a separate company, but then they kind of amalgamated. But you will find Wiltshire files and Nicholson files. They're pretty much the same manufacturer. I will put up a photo up here of the maker's marks of both Nicholson and Wiltshire. They're normally the ones to look out for. The ones to avoid are either unmarked files that don't have a maker's mark on them at all, or anything that's produced in India, Pakistan, that kind of thing. Test them, by all means. You may find that some of them have, got usable steel. That's why I gave you the test more than the name brand. But I know for a fact every Nicholson file, every Wiltshire file I have ever used to make something out of has been 100% high carbon steel. So that is the brand to look out for. Infarious Rust, Balota, and Save Edge are the two that I have used quite frequently, and both of them are very good. The older the file is, the more likely it is to be all high carbon steel. Anything from Sheffield in England, those are my holy grail of files. Whenever I get a Sheffield file, I always hold on to it until I have a good project for it. So, yeah, those are the ones to look out for as far as files goes. But let's get into heat treating. If you're a stock removalist and you're just getting started in the hobby, perhaps you're starting with a small workshop where you don't have a forge. This doesn't really apply to you because you can make knives without heat treating, and that's all you have to do is buy a file or find a file in the scrapyard, and then all you have to do is temper it. So basically grab the file, stick it in your oven at about 450 degrees Fahrenheit or 180 degrees, 185 degrees Celsius for 2 hours. Leave that nice long temper soak. And basically that's it, it's a tempered blank. And then as long as you don't get over temperature on your steel, if you don't start turning the steel blue when you're grinding it, then you've got a finished blade. And there is actually a maker out there who is famous for doing that, and that is Michael Morris. And I have one of his knives. It's a fantastic knife. But yeah, all he does is temper the files and then stock remove the knife out of it. So that is an option. But this lesson is for people who do want to forge their blades, or perhaps are using known steel that they have purchased in bar stock and are stock removing from, which hasn't been hardened, it's been spheroid annealed. So this is going to be a very basic intro to heat treating. This isn't going to be really in-depth. I may do one of those later if there's enough interest. So to start off with, I'm going to take you through running my gas forge. And this is a forge that is fairly indicative of most gas forges, and the reason I'm doing this is because this requires tuning. If you are running a charcoal forge to heat treat, you don't need to do this step. So you can skip ahead, and I will try and add a time link somewhere around here that will show you the next stage of the process. This burner is a Gamico large burner. I believe it's the Big Hit 4, and it comes with the burner, the flare, all of the hosing and the regulator attached, and I'll show you the regulator in a minute. But the most important part of the burner is obviously this and the ball valve. Now the ball valve is where I control my gas on and off. You should shut your bottles off at the tank, and I normally do. I've just turned it on because I know I'm going to be using the forge today, and I control most of my flame through the ball valve. And I can actually control pressure through the ball valve if I'm kind of in a hurry to change my pressure, but I normally do that through the regulator. So this is a Venturi burner, and it's quite common in most gas burner forges, unless you're using a blown forge, which case it's a totally different system and I'm not going to go into that. But for Venturi burners, basically there's only two things to worry about. That is gas pressure and air. And this is your air control, this little screw right here. The more open it gets, the more air you get. It's pretty simple. Basically all that's happening is that a high pressure jet of air is going through a little nozzle inside this cone, forcing gas into the burner tube, and that's creating a vacuum. As it shoots through, it's obviously sucking material with it, and that is obviously the air that's coming in from the outside. So the less space that air has to go through, the less air gets into the burner tube to create combustion in the chamber. So if you're trying to cool your flame down, one of the first things you're going to do is turn down your air. So when I'm running the forge for forging or forge welding or whatever, I'm normally running a full open choke. This is just like a choke on your engine, and I'm running a relatively high pressure, medium pressure, 25, 30 psi. For heat treating, I tend to turn it down to about 10, 12 psi, and I cut my air way down to probably about there, where there's just a little bit of a gap, but not much. And what I do with the regulator is I turn that pressure down, and I'll show you that now. So this is my LPG tank. It's obviously just a little, Americans would use propane, Australians we use LPG, liquid petroleum gas. And this is my high pressure regulator. A barbecue regulator will not do the job. It's too low pressure for Venturi burners, and it doesn't have any kind of adjustment. So this will go from 0 psi all the way through to 40 psi. How I know what my pressure is, as I screw in, the pressure goes up. As I screw out, the pressure goes down. The easy way to test that is to light the forge and then play with the regulator a little bit. This is actually fittable with a gauge if you purchase a pressure gauge separately. I haven't because I don't need to, because I know how to run this thing because I've played with it enough. But having a gauge on there makes it a lot easier to run your regulator effectively. You know how to control the air, you know how to control the gas pressure. Now all we need to do is light it. Now I use a matte gas torch, but you could just light a piece of paper on fire and stick it in there. Whatever you do, do not use matches or anything that you have to stick your hand in front of or inside the forge when you light it. It's pretty much common sense, but you know, that's that being said. So I've got the air set full out, and I've got it pressure set at about 15 psi. It's going to be a bit loud. So obviously if you've watched my YouTube videos before, you know that this is the sound you hear when I'm forging. This is running at the pressure that I would normally be doing light forging at, that medium orange temperature. If I was running forge welding, watch this pencil flame here. That's the most important part of the fire. This tells me what pressure I'm running at. At the moment it's about halfway down the forge body. As I turn up the pressure, that will extend. Touching the bottom of the forge floor, that is the highest temperature I can run. If I go beyond that and I start creating a cold spot on the floor, I'm basically just wasting energy to the outside of the forge. So, turned it back down to 15 to 12 psi, running that about half width flame. That's going to give me a nice neutral atmosphere when I shut off the air. It's a bit quieter now. It's exactly the same pressure of gas, exactly the same number of, particles of LPG going through, but it's not sucking air with it, so therefore it doesn't have the energy to really push a bright blue flame. At the low air, you will get what's called luffing, which is what happened with that forge just then. It's when the flame can't keep a solid stream. You don't want that to happen too much because that will really fluctuate your temperature. So try and get it to the point where the air is just low enough that you can still maintain a steady stream, but you're getting these nice tendrils of fire coming out. It's not very obvious on the video, but there is kind of a flames coming out to the top of the forge right now. So this is kind of the temperature we want the forge to run at when we're starting to do heat treating. But before I get into how we heat treat, I need to tell you what we're heat treating. Now in this case it's a file, but, and I specifically know this one is W2. I've had a lot of files spectroscopically analyzed. I'm still going to stumble over that word, guys, sorry. But it's been spark tested, which is actually, what they do is they ignite a small section of the steel and then analyze the vapor and the gases that come off the steel and the color of the sparks and stuff. There's a whole machine that does it for them, a computer that does it for them, and tells them exactly what the contents of the steel is. So I know exactly what steel this is, so I know how to heat treat it, but what makes a steel hardenable? The main answer is carbon. Now the thing is that there are steels out there that don't have carbon in them but are still very hard because they're alloyed with stuff like niobium and tungsten, that kind of stuff. So there are steels out there, but those will not harden in the traditional sense. They won't, you can't take them out and quench them and make them hard. They require different processes. But the very basics that you need for a hardenable steel is a iron piece with a carbon alloy of at least 0.4%. You can harden things below 0.4% to about like 0.25%. You can harden them to a very, very slight degree, but 0.4% is basically the bare minimum that I would say is required for hardenability. That's what I normally use for my hammers. I use chromoly steel, which is 4140, 41 being the chromium, and then 40 being the percentage of carbon, 0.4. So 0.4 being the lowest on the rank of hardenability isn't great for knives, and normally you don't want to start making knives out of stuff until you get up into the 1055 and higher range. So like the 0.55% carbon and higher. So 0.6 is good, 0.65, 75, 84, all that kind of stuff is great. Once you get past 1.2% carbon, it becomes cast iron. At that point, it's not hardenable, it's just brittle, and it's great for making cookware out of, but you can't make anything else that actually requires use out of it. So, piece of carbon steel. This is W2, so it's got a high manganese content, and it's also got a high carbon content. It's about 0.95 to 1% carbon steel. So, being that we know what this is, we know that we can harden it because it is in that range between 0.4 and 1.2. We now need to know how to harden it. So we'll move on to that next. So an important aspect of heat treat is obviously heat. And I'm using a gas forge today, obviously, but you could use charcoal, you could use a matte gas torch like this one, you could use a propane torch, but obviously with matte gas and propane, without something to contain it, like a small one brick forge, if you go on YouTube you can find many videos on how to make a one brick forge with a matte gas torch for heat treating, which would be very useful for a small home shop. You need to be able to heat this up. Even a wood fire will get it up to heat treating temperatures. Heat treating temperature, critical temperature, is the temperature at which the iron matrix becomes so fluid that it no longer has a magnetic field. There's a very complex technological, kind of explanation for that. I'm not getting into that in this video. But basically all you need to know is that once the steel gets to a certain point, a magnet won't touch it. Critical temperature for most steels, not all steels, but most steels, is just above critical temperature. Critical temperature tends to sit around 800 degrees Celsius, which I believe is 1475 degrees Fahrenheit. But critical temperature for most steel tends to sit around 820 degrees Celsius, or 1525 degrees Fahrenheit. So that is the basic temperature you're going to want for most carbon steels that you're heat treating. We're not talking about stainless steels today. They're a totally different subject. Carbon steels only. Simple carbon steels like 1095, like W2, like 52100 and 5160. So, we know that we need to get it up to 820 degrees Celsius, but how can we tell? The first way we can tell is by using a magnet. I don't actually have my magnet in my shop. I left it at the workshop that I teach at. But basically, once you get to the point where the magnet will not stick, you then heat it just beyond that, watching the color, and get yourself a good heat treating temperature. It's not the most reliable method, but it is a method that you can use. The trick to doing that properly is to continually test it as it starts glowing. The moment it gets that really dark red color, and I'd suggest doing this either at night or in an enclosed room where you can get as dark as possible, because any kind of ambient light, especially sunlight, is going to kill your color. You're not going to see anything. So when it gets that dark red heat, start testing. Because one of the things that I see a lot of people, the mistake that I see a lot of new smiths make with the magnet test method, is they heat it up to glowing orange and they test it with a magnet and they go, yeah, that's hot enough, and they stick it in oil. And the problem with that is that they've way overshot the critical temperature, because a steel becomes non-magnetic at critical temperature and stays non-magnetic all the way up till it's a puddle of goo. You know, when it's a fizzing mass of sparklers, it's still non-magnetic. So the trick is to get it just to that point of non-magnetism. So, you know, testing it constantly until it just won't touch the magnet, and then go a little bit further than that. Not taking it up to orange and going, yeah, magnet doesn't stick, and stick it in your quenchant. But that is the important thing with magnet tests. How do I do it? What I've done is I actually had a friend who had a laser temperature reader, and basically we worked out exactly where the settings on my forge will run at about 820 to 825 degrees Celsius. And that's the settings I've got right now. So I marked that on my regulator and I marked that on my air. Sometimes I have to fluctuate the air a little bit depending on if there's a cross breeze or something. But that's how I get my controlled temperature. And all I have to do is get the steel to get to the maximum it can in this forge. Just sit it in there and let it go. So that's how I control my temperature. The other way you can do it is, if you're doing the magnet test constantly, watch the color that you're doing. Every time you do that magnet test on a piece of steel, watch the color that it looks like when you're testing it and it's not touching the magnet anymore. And after a while, you'll learn that's what the color of the steel is when it's in your shop. And especially when you're only working in one position, that's really useful. You could use a temperature controlled kiln. That's an incredibly good way to do it. And if you have that, please use it. Don't think that forge heat treating is better. Temperature control all the way in heat treatment. Heat treatment is one of those things that I don't think we should be going all hands-on and mysticism on. It is a purely scientific process, and the more control you have, the better you're going to be. This is even with the setup that I've got where I can control my temperature, it's still not as good as an even heat or a Paragon kiln, or even a homemade electric kiln that is controlled by a PID controller. But with that being said, we'll now move on to the process, the actual process of heat treating. The first step of heat treating is to get this to critical temperature and let it cool down, especially when you're using unknown steels or you've forged the material that you're using. Annealed steel that you then stock remove, this step isn't entirely necessary unless you're grinding to the point where you're turning it grey. But with unknown steels, or with steels that have been previously used for something else, or if you've forged it, you have manipulated the grain structure, especially if you've heated it up, cooled it down multiple times. The grain inside the steel is going to be very large. In my last video, you noticed that the photos that I took were of the ends of snapped pieces of file, and the surface looked almost smooth. There was almost no grain structure. If I'd, zoomed that in quite a bit and had a better camera, you would have noticed very, very tiny granules. That's what you want in a good heat-treated blade. If you break a piece of steel that you've heat-treated and the grains look like beach sand, you've done a bad job. So this process is called normalization. It is not annealing. Annealing is heating to critical temperature and letting it cool very slowly. And that you can do with the gas forge very easily by just letting it heat up to critical temperature in the gas forge and then shutting the gas forge off and letting the forge cool down with the material in it. Or you can heat it up to critical temperature and stick it in vermiculite or perlite. I don't do that myself because I just tend to do the forge method. But normalization simply relaxes the grain structure. All of that stress you've put into it through the forging steps or through the manipulation steps, or if it's an unknown steel, relax that grain structure, shrink those grains, and make it a much finer piece of steel. And the big thing for this is the main reason that you want small grain structure is that large grain structure is very brittle, and it also means that you imagine that you made a knife out of rice bubbles embedded in Play-Doh, right? This is a weird description, but imagine it. If you were to scrape that on something, the rice bubbles would pop out of the edge, yes? Because they are large and only lightly held onto. That's what happens in a knife edge with large grains. The grains just pop out. And so you'll chip your edge no matter how well you temper it. Whereas if you made the same thing using beach sand and Play-Doh, or beach sand and some other kind of thing, you may still get a loss of grains, but the grains will be much smaller, and that's the case with steel. So that's an important thing to keep in mind, is that you want to relax the grain structure. Normally when I do a forged blade, I will normalize 3 times. In this case, because I'm just taking this file, which I've never manipulated before, it is hardened at the moment, but because I haven't done anything with it, I am going to do 1 normalization cycle for the purposes of this demonstration. If I was to normalize this or anneal this for stock removal with files or something like that, if I was making this by hand at home, I would probably do 2 or 3. But now I'll get onto that and I'll show you heating it up to critical temperature. So there we go. Now it's going to look a little uneven on the camera because the camera picks up infrared light a lot easier, which is why steel glows. It's the infrared light that comes out. So one of the big things with normalization, some people I've seen on YouTube will wave the steel around to try and make it cool faster, but that kind of defeats the purpose of normalization. The whole idea of normalization is to let it relax and cool slowly in still air. And if you're waving it around, you're actually air quenching the steel, which if it's high enough carbon, it'll actually quench it somewhat. So the main thing is to keep it still. If even better would be to put it on some refractive bricks or refractory bricks. What you don't want to do is put it on a cool surface like your anvil. If your anvil is nice and cold and you put a piece of flat steel on there, what's going to happen is that this side's going to cool faster than this side, and it's going to contract, and you're going to end up with a banana for a piece of steel, even though you haven't quenched it, it hasn't warped. Now, because this is a half-round file, it actually has warped somewhat, because the big flat side is cooling faster in the air than the round side is. And that's something to be careful of. That's why when you're pre-grinding, if you're grinding before heat treat, you need to make sure everything's nice and even and flat, because any discrepancies is going to cause warpage. And this is warping during normalization, which is something that a lot of people don't talk about. When you quench, a lot of people talk about quenching and stuff like that, and they say, oh, you got to be careful of warps during quench. Sometimes the warp will happen during the normalization cycles, and people don't notice because they're not looking for it during normalization. All they're doing is, kind of putting it on top of their forge or, whatever. They're not really looking at the piece of steel. And then when it comes to the quench, they quench it. They go, oh no, it warped in the quench. It may have actually warped during normalization. So this is the time to check your straightness, make sure that everything's in line. If there is any discrepancy during the next normalization heat, tap that thing straight. It's at a heat where it will move slightly, so tapping things straight at that temperature isn't really going to affect the grain structure or anything, but you can get it back straight a lot easier. You could do it cold, but then you're risking cracking it, because high carbon steels don't like moving when they're cold. So, now that this is basically normalized, the normalization doesn't require it to go to room temperature. It just requires it to go back through the recrystallization process, which I've tried to capture on film before. I will try and capture it in the future, but you can, in a dark room, dark, like pitch black, if you heat to critical temperature and let it cool and watch it, you'll actually see the heat recede and then another, almost like a shadow of heat, pass over it again. It's called recoalescence or decoalescence and recoalescence. So that's a really good sign that you've got it all past the critical temperature. But basically, this is now completely normalized. I still wouldn't want to touch it because it's still sitting at around 600 degrees, maybe 500 degrees Celsius. Sorry, not Celsius, Fahrenheit. About 230 degrees, 240 degrees Celsius. I'm going to keep trying to do that, but if I get it wrong, I apologize. But yeah, so it's still quite hot, but this is now normalized, so it should be nice and soft. And the best way to test that would be to bend it. I'm not going to do that because I know it's soft, but you could, if you wanted to test your normalization skills, bend it. If it snaps, then you've either not normalized it enough or heated it way too hot and then waved it around and tried to cool it. If you overheat during your normalization cycle just with your quenching cycle, don't just think, oh, it'll be okay because it has to go down through that recoalescence phase anyway. If you've overheated, you've grown that grain structure. You're going to have to do another normalization cycle. Sorry to say it, but it does happen. That's why I like having temperature control, is because you can overshoot way too easily, and then once you've overshot, you've got to restart. And if you don't restart, you're risking having problems. So, now this is normalized, we're going to talk about quenchants. There are a lot of different kinds of quenchants out there, ranging from high quality, high cost, professional heat treating oils, all the way down to water. But all of them perform exactly the same process, which is cooling the metal down at a speed at which it will crystallize into martensite rather than going into perlite or ferrite. Which means it's going to get hard rather than soften. And that's what we just did. We just softened a file because we heated it up and then let it cool slowly enough that it hit the perlite phase rather than the martensite phase, which there is actually a really good video on YouTube, a short excerpt of Kevin Cashin talking about heat treating 1084. I highly recommend you check out Kevin Cashin. He is the master when it comes to heat treatment. But if you can purchase his DVDs, do it. Oh my god, he is amazing. But the basics of it is if you cool steel really quickly, you will form martensite. If you cool it really slowly, you may miss the martensite, which is why clay on the spine of knives and stuff works, because it closes it down slowly. But I'm going to cover the quenchants that I regularly use. The first quenchant is actually attached to the side of my forge, which is this pipe right here, which a few of you may have seen in my previous videos me use, is oil. Now, I don't use a high quality quenching oil. I should, but I don't because I can't afford it at the moment. I will eventually in the future. At the moment I use rice bran oil. Now the reason I use rice bran oil is because it's got a very high flash point. The higher the flash point of the steel you're using, the better. Peanut oil is also a very common one. It all is about the smoke point and the flash point. The reason a lot of people will have heard don't use used motor oil, because it was very common for a while to use used motor oil or motor oil in general, is because it has additives that create a lower smoke point. It's all about, you know, making the fluid dynamics of the oil better at heat so that it provides better lubrication, which is great for a car, not so good for quenching. Now, any oil quenchant is going to create carcinogenic smoke. So try and do it in a cross draft if you can, wear a respirator. All of the safety concerns that you have with grinding dust and stuff like that should be taken with oils. That doesn't matter if it's food grade or not. You burn oil, you're burning carcinogens. Just a heads up. It doesn't matter how good the oil is, doesn't matter how healthy it is, it's still carcinogenic. But being that this has got a really high smoke point and a really high flash point, it doesn't smoke as much. Quenching oils, proper quenching oils, Parks 50 and Horton's K and Horton's Q and all that kind of stuff, have an incredibly high smoke point, an incredibly high flash point. And they're designed that way so that they don't let off all of that really nasty smoke. Oil is it can be a fast quench, or it can be a medium quench, or a slow quench. It all depends on the viscosity of the oil and the ability of it to remove heat from the steel. Rice bran oil, when heated to around 60 degrees Celsius, which is what you should preheat all oils to when heat treating, because it decreases the viscosity, means that it flows easier, removes heat. It's actually kind of counterintuitive that way. Rice bran oil is kind of a medium speed quench. So it doesn't cool it down super quick, but it does cool it down faster than, say, a really high viscosity oil like motor oil would. The big problem with medium speed quench oils is that if you're using super high carbon steels or shallow hardening steels like W1, W2, 1095, those high carbon steels, they may not get as hard as you will get with a high-speed oil like Parks 50. That's why I want to get a high-speed oil eventually, is because I use a lot of really high carbon steels, and Parks 50 would be amazing for that. But there is a higher speed quenchant, but it is incredibly dangerous for your knives, and that is water. Now I have a barrel of water off to my side. You guys will have seen it in previous videos. If you haven't, you know what a barrel of water looks like. Now bog standard room temperature tap water will quench your steel, but it quenches it so quickly that it will actually create stress in the blade, which could potentially crack it. Now I do a lot of water quenching for harmones and stuff like that when I'm trying for a really fancy pattern or something, or when I'm looking for a really, really high hardness, like on my Japanese Sen scraper. I went for a water quench, I believe, in the video. If I didn't, I actually re-quenched it in water afterwards, just to get that super high hardness, because the faster you get it below the martensitic line, the more martensite forms, and the more martensite that forms, the harder it is. So, water is a viable option. I use it for 4140 for all my hammers. I quench in water these days. It's very usable for the low carbon steels. The lower the carbon, I find, the easier it is to use water to heat treat them, because it doesn't affect them as much. They don't form as much martensite because they don't have as much carbon in them. But there is an even more extreme version of water that can be used for quenching, and I use that when I'm making axes out of 4140 or various cutting tools out of low carbon steel, and that is brine. Now with brine, all you're doing is mixing salt and water. It is literally just sea salt water. The best way to get a good brine is to see if it can float an egg. Now, it has to be an egg that's good, because a bad egg will float anyway, but a good egg should sink to the bottom of water. If you've got enough salt in that water, it will float a good egg. And if that's what you're doing, then you've got good brine. The other thing you can do with brine to make it even better is to add a little bit of dish soap, which is a surfactant which kills the surface tension of the water, which means that it's going to cling to the steel that you put in there a lot faster, which means it's going to cool it down even quicker. So, and some people refer to that as super quench. The dish detergent or the laundry detergent that some people use is a surfactant that kills surface tension, and that just helps it cling better. I don't tend to use that in my brines because salt and water just tends to do the job for me, but if you really need that extra level of hardenability, then you can do that. But yeah, today we're going to be using oil because I'm not looking to harden this thing to use it with anything, but oil is also the safest method of quenching pretty much any steel out there, because it's not going to overstress the blade. And it's relatively easily accessible for most people. If you just go to your local supermarket, you can probably buy a quart or a gallon or 4 litres for Australians or people in the UK of rice bran oil or peanut oil or corn oil or anything like that. So, the next step, we're going to heat it up to critical temperature, just past critical temperature, into that hardenability range, and then we're going to quench it in oil. But before we do that, we're going to preheat my oil, and all I'm going to do that is I've got a very old and dirty railroad spike. I'm going to heat this up to a bright orange color and dunk it in there, swirl it about. And normally what I do to test my oil temperature is just dip my finger in it. If it's hot enough that I kind of go, ooh, that's a little hot, that's good. It's a very unscientific approach to it. I should probably have a thermometer in it. And if I was doing a knife, I probably would. But when I'm in a hurry, I just, do the finger test. It's the easiest way to do it. But yeah, so we're going to get onto that now, and I'll come back to you when I'm ready to quench. Preheat the oil. Stirring it up to get all that temperature through all the oil. And I've just thrown the file in to start heating up. And quickly into the oil. You don't want to mess around with it when it's sitting that high. The big thing is if you take too much time in going to the quench, you're going to end up with the outside or the thinner parts of your blade, the bevels and stuff like that, the tip, cooling down to normalization temperatures before you get to the quench. And if that happens, you don't end up with a hard blade. You just end up with, you end up with a hardened back and a soft edge, which is exactly the opposite of what you want. But normally, if you've done your job correctly, if you've moved quickly enough, you got to the appropriate temperature. I'm not sure how obvious it's going to be on the camera, but there is a very slight grey popping through in places where the scale has popped off. And that is a spectacular sign that we have formed martensite. It's not proof, it's not evidence that we've formed martensite, but it is a spectacular sign that we have done our jobs correctly. If we get that grey patination, it would be a lot more obvious if this was flat, because it would actually, pop off more scale. Being that this is a file textured face, it's holding onto it a lot better. But I can see that there are portions of martensite in there, so I know that I know because I've done this before that I've successfully made martensite. But for you guys, that's a really good sign that you've done your job. But next, we get on to testing whether it's hard. So I've locked it in the vise, and normally I lock my blades in the vise vertical so that it helps them cool evenly on both sides. Again, you do not want to lay this on something cold on one side because that could help it warp. This file has warped because it is a half-round file. As I said, this side was going to cool faster than this side anyway. And the important thing is, this is only like 20 seconds after the quench. I've just moved the camera. But it is already cool enough that I can touch it. The reason for that is because I let the steel cool down to oil temperature inside the oil bath. Now, if I wanted to tweak this, I could have, if I'd only quenched for about 4 seconds or 4 to 6 seconds, and then, done some tweaking outside of the forge and then gone back into the oil. That's a more advanced technique. In this case, we're just going straight from the quench to testing for hardness. So, I've quenched it, I let it cool down to the oil temperature, so the same temperature as the oil, about 60 degrees, and now I've locked it in the vise. And the way we're going to test it is I've got the broken file from last video. I normally have an old file or something like that lying around, and I'm just going to try and cut it. Now the important thing is, if you drag your file backwards on the steel, I see a lot of people doing this when they're testing the hardness. They'll drag the file backwards over the edge of a piece of steel to test the hardness. That doesn't tell you anything because files only cut in one direction, and that is away from the tang. So this is the tang of the file. It only cuts in that direction. So you really want to go at it, which is why I use a old file. I don't care if I damage it. I want to know, can I remove material, which in this case, I can't. Now, if you're using a charcoal forge or a gas forge or something like that, and you're not using a neutral atmosphere, so you're creating a lot of scale when you're heat treating, you may have a layer of what's called decarb or decarburization. That is where the carbon has leached out of the iron into the scale and then escaped the steel in scale. That's why I go so aggressively at it when I'm testing. Because if there is a layer of decarb, I want to cut through that decarb. If I just kind of, oh no, it's soft, I may actually only be scraping the surface of the decarburization, and I've done that a few times. And then right underneath that is the hardened steel. And I've actually reheat treated blades that I thought I'd failed to heat treat, only to find out that it just had a layer of decarb, and I'd further decarburized the steel in the second heat treat. So make sure you go at it, get through that layer of decarb, especially on thin portions, and see if it escapes. If you can cut down with a corner of a file, if you can cut a notch in it, then, if you can cut a notch, which I can't with this, then you're obviously, need to go back and reheat treat it. But in this case, this is 100% hard. This is harder than the other files. So we know we successfully hardened this, but it's not usable now because it is entirely brittle. If you think back to the last video where I broke a file in the vise when it was unheat treated, or it had been heat treated from the factory, it snapped quite readily. So what I'm going to do is stick the point in the vise and just give it a little tilt. I don't need my... There we go. And broke it. And You won't be able to see it in the camera because it won't focus that close, but the grain structure is beautiful. It is nice and fine, and that's mainly because it was already a nice fine grain structure from the factory, but I also did that normalization cycle before I did my quench, and I controlled my temperature. And I suggest, if you're just getting into bladesmithing, do some test pieces. Don't even make a blade out of them. Just, forge a piece into something, heat treat it, and then check for your grain structure. Get your grain structure dialed in. But I can tell that I did a really good job on that. That is solid heat treat or solid hardening. But as you can tell, that is really, too brittle. So now we need to temper, and there are two methods for that. We'll get into it. Okay, so off camera I just further broke down the file, just one more step. And this is because we're going to use both tempering methods just to show the difference between the two. Now in both methods I want to be able to show the oxidization colors, the heat treating colors, on the surface. What I'm going to do is just take the grinder to it and grind the surface of the steel clean. If you don't have access to an oven, which is one of the methods, then you're going to need to do this anyway because you're going to need to be able to see the colors when you use a torch. Alright, so I've cleaned the steel. I've only cleaned a portion of it. I don't need to worry about too much because we're just going to show the colors on this. And what we're going to do is set the oven to about 180 degrees, and we're going to put it on for an hour. Normally I would do a 2-hour cycle and then cool it to room temperature and then another 2-hour cycle. The time at temperature does actually have an effect, but we won't get into that today. And basically all I'm going to do is set it in the oven, nice and even, and close the door. If you want to get a better, more even heat on especially very thin pieces which you worry might unevenly heat in your oven, put it in a tray of sand. Just get some normal play sand or normally backyard sand, as long as there isn't wood and stuff in it so it doesn't burn. And then stick your piece on top of the sand or in the sand and heat it for that 2 hours, and the sand will act as a heat sink for the temperature and actually even it out a lot better. I'm not particularly worried about that in this case, but it's a really good technique if you've got especially large blades which might sit in different positions in your oven which may be uneven, because a lot of home ovens tend to be very uneven heaters. So the second method of heat treating is what's called flash temper, flame temper, torch temper, or forge temper. They're all exactly the same thing, they just sometimes use different methods. In this case I'm going to be using my matte gas torch. You could use the dying embers of your charcoal fire, or you could wave it in front of your gas forge to build up the heat. But basically all we're trying to do is reheat this steel to a much lower temperature than critical temperature to bring back some of the toughness, the springiness of the steel, remove some of the hardness, but you get a much more usable piece. Now the important thing for this process is to have clean steel. Very clean, like acetone the surface. This has come straight off the grinder. I haven't touched the surface at all, but any oils, any fingerprints or anything like that will affect the color that the steel turns. So it's very important to have clean steel for this process. I'm touching the back, but I'm not touching the area that I've ground. So all we're going to do is I'm going to heat the bottom of this. I'm going to watch the colors run. Now in the case that I was tempering a blade, I would want to paint the heat very carefully, especially in the thicker areas, and try and get an even golden bronze color. But in this case, what I'm trying to do is show the graduation of colors from that straw, the very light yellow, all the way through to the peacock blue, the purple, the brown, and the gray. So we'll do that now. Unlike in quenching, when you're tempering, you can quench straight after you temper. That freezes the temper. So if you're having the temper move a little too fast, it's going into that blue phase, just stick it in water. It's not going to hurt the steel. Doesn't matter what kind of steel you're using, that's not going to hurt. Okay, so we've got the two items out of the temper. I'm going to put a photo up here. You'll notice that the oven tempered one, it hasn't got as much of a colouring to it because I only tempered it for half an hour, and also because it was in the environment of the oven, the oxygen was actually getting expunged to a certain degree, so the oxides didn't form as well. It actually started to colour a little bit more after I took it out of the oven than it was inside the oven. But the important thing to note is, obviously, the temperature range on the torch tempered one is far more variable, but that's on purpose. But it also demonstrates how easy it is to overshoot the temperature when using a torch temper or forge temper. And if you overshoot the temperature, then you've softened the blade or the cutting tool, whatever you're trying to make, too far, and therefore are not going to get the edge retention that you would get otherwise, and so therefore you're going to have to go reheat treat, which, re-quench, re-temper, and renormalize before quenching. And that can be a massive pain in the butt, whereas with the oven temper you don't have that risk. You throw it in the oven, you leave it there, it's done, and that's it's spectacular. Now, that isn't to say that torch tempers don't work. They do work. They've been used historically for centuries effectively, and there's nothing saying that they don't. The only thing about that is, it is normally uneven, especially the torch temper. You tend to have hot spots and cold spots, hot spots being thinner and normally towards the edge, which is normally a very bad thing. And also, they tend to only be on the surface. So the whole idea behind coloration in steel is there's a thickness on the microscopic layer, on the microscopic level of the layer of oxide that develops on the steel when it's heated up. So the thinner the layer, the lighter the color. And basically what that does is that the reason that that happens is because the light is reflecting off of that material, and certain wavelengths are being sucked in, whereas certain wavelengths are being bounced off. That's why most leaves we see are green, but they're actually not actually green themselves. It's just that that's the only color that reflects off the leaf. The leaves are actually yellow or some form of brown, but they suck in all of the red and the blue and all that kind of stuff, and only give us the green reflection back. So that's the same thing with this. When the oxide layer is very thin, it reflects back the yellow colors in the light that's reflecting off the surface. And as that scale builds up, as that oxide builds up, it slowly darkens and then turns that purple, the blue, and the gray. And that means that you can have a false reading. Now, I get that with oven tempers sometimes. If I've cleaned a piece of material before I temper it in the oven, if you leave it in there for 4.5 hours or 5 hours at 180 degrees, although the temperature has not changed, you may have a blue blade when you pull it out. It may look that color, blue. And the problem is that could tell you, oh my god, I've over-tempered it, it's way too soft. The fact is that that's not true. It's just the fact that staying at heat for so long has meant that it's actually developed a thicker oxide layer than it would have otherwise. It's still at the same hardness it was 4.5 hours ago, or, it was still the same hardness as it was after the temper had reached the center of the material, which is the other thing about torch temper. Torch tempers tend to only do the surface if you do it once. Most old blacksmith books tended to tell you to temper 3 times. If you quenched a chisel, for instance, you would quench the chisel, scrape the scale off really quickly, you'd quench just the tip, and then scrape the scale off really quickly, watch the colors run, quench the tip, scrape the scale off, watch it run again, and do that as many times as you could before the heat ran out of the body of the piece. And that was because they understood that it was only on the surface that the heat was coming from. And that's even more prevalent in torch tempers or forge tempers where you're waving it in front of the forge. The surface may get to that tempering temperature, but the center may not. And you can't just leave it to permeate, because sometimes you're going to overshoot that if you leave it for too long. So you've got to stop the temper and then go back and re-temper. So if you're going to do a torch temper, I would recommend doing it at least 3 times and swapping sides between. So if you do it this side first, you get that all to a nice straw color. You flip it, you do the second side, and in between you quench, and then you do the third side again, or the same side again. And that will just guarantee that you've got the temper all the way through the piece, and that's going to give you a better result. On large chopping knives and stuff like that, you may want some blue and some purple on the spine to give you a little bit more springiness in the piece. Some people accomplish that through differential quenching, so using edge quenching or something like that. There are certain issues with that as far as metallurgical things go, given that there's a very distinct line between hard and soft, and that tends to mean that you can have a shear line. And I've actually seen blades that the quenched portion had snapped away from the unquenched portion because the line of ferrite and the unchanged austenite has ripped away from the martensite that's formed. So that can be dangerous. Whereas tempering back from the spine is a really good way to go. Actually, on large knives, I tend to quench fully, oven temper, and then sit the edge or the area that I don't want to be tempered in a bath of water, and then temper the spine back with a torch. And that's a really good way to get a spine temper, a spring temper on the spine without overheating your edge. But that being said, that is the basics of heat treating. That is everything you need to know to get started in heat treating. I may do a more advanced class on heat treating in the future if there's enough interest. And hopefully you guys learn something. That's what I'm here for. I'm trying to share as much of my knowledge as I can. If you feel that I was wrong on any points, feel free to leave that in the comments. I'm always willing to be proven wrong. Just make sure you have evidence and not anecdotal evidence, because it's more a science than a mythology at this stage. With that being said, I really appreciate you guys watching. I hope you enjoyed it, and I hope you learned something again. I would like to take a moment to thank my patrons. My top patron, Jared Russell, again, an awesome guy. But Nathan, Andy, Kine, Rich, and Braden, you guys are all fantastic people. You keep me going. You keep gas in the tank, and unfortunately no hammer in my hand, but lots of words coming out my mouth. I appreciate you guys taking the time to listen to me ramble. I hope you have a fantastic week, and I will see you tomorrow on my live stream at 9 a.m. Australian Western Standard Time. With that being said, have a good one, guys.